Welcome to the podcast on speed, velocity, and acceleration. You're going to be learning the difference between speed, velocity, and acceleration in this podcast. Before going any further, we need to understand that motion is relative. If somebody talks about a space shuttle moving 8 kilometers per second, that's relative to the Earth. A race car might be going 300 kilometers an hour, that's relative to the track. You might be sitting in your desk at class, and compared to everybody else in class and everything around you, you're not moving. You've got a speed of 0 kilometers per hour. But relative to the sun, you're actually moving at 30 kilometers per second. So is everyone around you, all the air around you, all the buildings around you, everything's moving around the sun at a certain speed. Beyond that, everything's moving around the galaxy at an even greater speed around our galaxy. So motion is relative. Unless otherwise stated, the speed of things in our environment are measured relative to the surface of our planet. So the next time somebody gets on for you for sitting still and not doing anything, you tell them you're moving at 100,000 kilometers per hour relative to the sun, and so were they. Speed is a measure of a distance over a measure of time. We read the division sign, the slash, whatever you want to call it, as per. So any distance per any unit of time. Miles per hour, kilometers per second, centimeters per day, light years per century. Anything where you have a unit of distance over a unit of time, you got speed. Now the most common units we're going to use are going to be meters per second. So for example, if a cheetah can cover 50 meters in a time of 2 seconds, a little math will show you that that comes out to be 25 meters per second is the speed of that cheetah. Some common speeds for some everyday objects are shown below, and they're shown in miles an hour, kilometers per hour, and meters per second, which is the unit that we're going to be using in physics. The most common unit we're going to be using, or units, is meters and seconds. The speedometer in your car has measurements both in miles per hour and kilometers per hour. And this also, the speedometer, it measures your instantaneous speed. It does not tell you your average speed. It tells you the speed you're going at that particular instant in time. For example, if you're driving in a car and you cover 240 kilometers during a time of 4 hours, your average speed was 60 kilometers an hour. That does not mean that you were driving 60 kilometers an hour the entire time. It was an average. Sometimes you were going faster, sometimes you were going slower. So a lot of times when we're dealing with speed, we're talking about the average speed, which is the total distance covered divided by the total time it took to cover that distance. As with any three-variable equation, if you have two of the variables, you can solve for the other one. So if the speed, signified here by an S, is equal to the distance divided by time, you can solve if you know the distance covered and you know how long it took. Also, let's say that you know the average speed and you know the time, you can find the distance. In that case, it would be the speed multiplied by the time equals the distance. And if what you're trying to find out is how long it's going to take, you know your average speed and then you know your distance, then that becomes the time equals the distance traveled divided by the average speed. Three variable equations. Now that you know something about speed, we're going to add a term called velocity. The only difference is speed is just talking about a magnitude, an amount, how fast something's moving. Velocity is talking about speed in a given direction. So instead of saying the car's moving at 60 miles an hour, we might say the car's moving at 60 miles an hour due north. Now, if something is traveling under constant velocity, that means its speed is not changing, and neither is its direction. If the speed changes, either speeding up or slowing down, or the direction changes, as in you're going around the curve, then you have changing velocity. Constant velocity means constant speed and direction. If you don't have constant speed or direction, you do not have constant velocity. For example, if you're in a car going around a circle, even if your speedometer is staying at 30 miles an hour, you are not increasing or decreasing your speed. You do have changing velocity. That's what's known as acceleration, which we're going to get to in a couple slides. If you are changing directions, you are changing your velocity. The rate that velocity changes is called the acceleration. So if you have a changing velocity, you take that change in velocity, divide it by the time interval, and you have an acceleration. Now, acceleration can be positive or negative. Negative acceleration is often called deceleration. In a car, for example, you have three different parts of it that can cause acceleration. You have the accelerator pedal or gas pedal, the brakes, and also the steering wheel. Any of those can cause a change in its state of motion, change in its velocity, which is known as acceleration. Now with this car, you got a driver in the car approaching a cliff. He sees the cliff, he applies the brakes, and the acceleration changes direction. And you can see that here, this red arrow is now going in the opposite direction. That would be a deceleration state. The direction is still the same, but your acceleration is different now. Once the car goes off the cliff, the direction of acceleration again has changed, and now it's due to gravity pulling it down, and the direction has also changed. Another important thing about acceleration is, since acceleration is change in velocity over time, your units come out to be something like this. In the case where you have something that's traveling at a certain amount of meters per second, there's a change in the meters per second. The acceleration would be meters per second over a certain amount of time. We could also measure that in seconds. In this case, what you end up having here is meters per second squared. So if something was traveling and accelerating and it changed how many meters per second it was traveling in a certain amount of seconds, we would read that answer as whatever unit, whatever number, and then we would say meters per second squared, or meters per second per second. Let's say that something is traveling at kilometers per hour. Here something is traveling and it changed from 0 to 10 kilometers an hour in a certain amount of seconds. We would read this as 10 kilometers per hour per second. Now, like we've already done for a few examples, we're going to do here as well. Imagine there's no air resistance. There's no friction. There's no resistance. You can stick your hand out of a moving car 100 miles an hour and you don't feel any wind resistance on your hand. If something is falling and there is no air resistance, in physics we say that is under free fall. That is different than if you're talking to somebody that's a skydiver. To them, free fall means the time they experience falling before they open their parachute. True free fall, as we're going to define it in this course, means an object falling where the only force acting on them, making them move, is the gravitational force, would be free fall. So there would be no air resistance, just the force of gravity pulling them towards a larger object. On Earth, the force of gravity works out to be just about 9.8 meters per second squared in the absence of air resistance. What we're going to do in this course is round that up to the much easier to work with 10 meters per second squared for our calculations. Now, if we do end up doing a lab that requires as precise measurements as we can get, you would want to revert back to the 9.8. But for the calculations we do in the book, and for talking about what's going on, we're going to use 10 meters per second squared when dealing with the gravity on Earth. Now, what it means to be accelerating. For example, if something is dropped on Earth, after the first second of fall, it's going to be going 10 meters a second. After the second of falling, it's going to be at 20 meters per second. After the third second, 30 meters a second, and so on. And that can be neatly expressed in the formula velocity equals g, which represents Earth's gravity, multiplied by the time the object has been falling for. So if an object is falling and it's been falling for 2 seconds, you use 10 for g, and you use 2 for the time, and that works out to be a velocity of 20 meters per per second. Something else that happens that's pretty neat with this is when you bring your units in, which you should always do with your calculations, is if you have something falling at 10 meters per second squared, and it's falling for 2 seconds, when you go to do the math, that cancels out, one of the seconds here cancels out, and what you're left with is an answer that's in meters per second, which is what you're looking for, which is a velocity. And again, here's a chart representing what we just went over. If you want to know the instantaneous velocity of something after it's been falling for a certain amount of time on Earth, you simply multiply how long it's been falling by the force of gravity. In this case, on Earth, you would multiply it by 10. Now, let's say you have something starting with a certain speed and you throw it against gravity. In this case, you can consider gravity to be negative, and you're throwing something in the positive direction. So if you start with a ball and you are throwing it at 30 meters a second up, after each second it will have lost 10 meters per second of its speed. So if it's traveling at 30 meters per second, a second later it's at 20 meters per second. After 2 seconds it's at 10. After 3 seconds, the velocity of that ball, the instantaneous velocity, is exactly 0. Then, as it starts moving back down, after 1 second of falling, the 4th second of this total throw, it's back at 10, then back at 20, then at 30. Right where you launched it, it's back at 30. And then if it continues to fall, each second it's going to gain. By the time it hits the ground here at 7 seconds, it's going 40 meters per second. So notice something else interesting here. The speed that this person is throwing the ball up at, 30 meters a second, it takes 3 seconds to lose all of that speed and be at 0. 3 seconds later, it's gained all that speed back, and it is back at 30 meters per second. This, again, is in the absence of air resistance. Hopefully here, you've noticed that while the speed increases and decreases at a steady pace, every second it gains or loses 10 meters a second, the distances are not staying steady. And that leads us to our next question, where we're not going to ask how fast something's going after a certain amount of time, but how far has it traveled, or how far will it travel after a certain amount of time. So this is an excellent time to take a break and maybe play a little game, get a little rest, get on Facebook and Twitter and mention how much you are enjoying learning about physics. Then sit back down a little later and learn about how far something has gone after a certain amount of time of free fall. Okay, welcome back. Earlier we discussed how you can tell how fast something's going after a certain amount of time, and we talked about how to calculate average speed. Average speed was the distance covered in a certain amount of time. Let's say that you wanted to solve for distance. Let's say that on this rock you're not looking at the speedometer, you're looking at the odometer. So we want to find how far it's gone. Another way to look at this equation is saying that the speed or velocity multiplied by the time is equal to the distance. And as something is falling, gravity causes it to accelerate. So it's traveling 10 meters a second, then 20 meters a second, then 30 meters a second. So the speed is going up after each second. That means the distance is going up as well. But it doesn't go up at a steady pace. It goes up exponentially. To find out how far something has gone after a certain amount of time, there's another formula that we need to use. And this is the formula, the free fall distance formula. If you want to know how far something has gone after falling for a certain amount of time, this is the formula you use. If you know how long the object has been falling, how much time in seconds, you know the acceleration, in this case the force of gravity on Earth, which we're going to round to 10, you can find out the distance. In the case that you have the rock falling and you want to know how far it's gone after a second instead of how fast it's going, you can simply plug and chug. Here for G, you make that 10 meters per second squared. Multiplying that by 1/2 gives us 5 meters per second squared. So here we got 5 meters per second squared. Done with this part. Multiply by time of 1 second squared is 1 second squared. Multiplying this out, your seconds squared cancel out, and what you're left with is 5 meters, a unit of distance. Again, we're looking for a distance that's measured in meters. Our seconds cancel out. If you were left with something that was in meters per second, that tells you something was done wrong. So that's one clue if you are doing the math right or not. If your units end up being what you want them to be, that's good. If you end up looking for a distance and you get the unit in time, or you end up looking for a time and you end up with a unit of distance, go back and check your math. Here's a chart expressing the free fall distance formula. After 1 second, the object will be going 10 meters a second, but the distance it's gone will only be 5 seconds. And if you think about this, it makes sense. It's accelerating 10 meters per second every second, but it's starting from a speed of 0, and it takes time to get up to speed. So after that first second, it has only gone 5 meters. After the second second, it's gone 20 meters. After the third second, 45, then 80 after the fourth, then 125 after the fifth, again ignoring air resistance, and that becomes the formula. Plug in whatever time for t and multiply it using the force of gravity on Earth, and that will tell you how far an object has traveled in free fall on Earth, or any planet. On Earth we use 10. If you were on another planet, you would use another value for gravity. So in summary, these are two very important formulas that we're going to be using the rest of this unit, the rest of this course. One quick note on these is that both of these formulas assume that the initial speed is 0. That means it's starting from rest. They also assume that the acceleration is constant. And on Earth, the acceleration is constant. So again, these two formulas, when you're trying to find how fast it's going and you're trying to find how far it's going, this is starting from an initial speed of 0 and constant acceleration of 10 meters per second squared on Earth. You've got your velocity formula that tells you that after a certain amount of time, how fast something is traveling, its instantaneous speed, and then you've got the distance formula if you're looking for how far something has gone, or if you know how far something's gone and you're trying to find out either the acceleration or the time it's been falling for. Those are two very important formulas that you do need to get familiar with. Now, it is important to understand how you can graphically represent some of these things we're talking about. Here's a speed versus time plot. On the y-axis, you have the speed in meters per second. On the x-axis, you have time. And this makes a straight line that progresses up at a steady pace. The slope of this line is constant. And something else that you might notice about this is, looking at the slope, you have a rise here from 10 to 20 over a time of 2. So here you've got a speed, a change in the speed over a change in time. And what is change in speed? I'm going to use the delta sign to denote change. Change in the velocity over a change in time, and that equals acceleration, or more correctly, lowercase a. So what you have here is a slope that represents the acceleration. So again, the rise over run on a speed versus time graph equals the acceleration. And we also say this is direct proportion. The change in speed and the change in time are directly proportional to each other. There is no exponents in this equation, is basically what that's saying. It's the velocity equals gravity times time. Now, a graph of the distance over time is a distinctly different graph. It gives you a parabolic curve. showing that the distance is increasing exponentially as time goes by because the instantaneous velocity at each point is greater and greater. This is an object that is accelerating. It makes an exponential curve. Okay, last slide. A couple of things I want to make sure that I get in here is that in these formulas we're using G. It can also be considered A, which is acceleration. On Earth, the acceleration is always 10 meters per second squared, so you can use those interchangeably now. If the acceleration was not caused by gravity, if there was some other force causing the acceleration, you would want to make sure that you put A, not G in that case. Now, another thing to note, these formulas that we're using, the formula for speed of free fall, velocity equals gravity times time, and the formula for distance equaling 1/2 gravity or acceleration times time squared. These are both assuming that the initial velocities were 0. These objects started from rest. Something else that you'll notice, hopefully, that is missing from these is neither of these equations have a unit for mass. If you ignore air resistance, which is what we've been doing right now, is assuming that there is no friction due to air resistance, then the rate at which something falls and how far it falls after a certain amount of time is independent of its mass. In this case over here, where you have a vacuum chamber where there's no air resistance, a feather and a coin will fall at the same rate. And we have one of these at school we will be experimenting with. In absence of air resistance, how far something falls and how fast something falls is independent on the object's mass. The only reason it doesn't appear that way on Earth is we have air resistance, and we will be getting into that later on. If there's anything in here that you have questions on, feel free to get on Facebook, Twitter, email, write them down, bring them into class, watch this a couple more times, and we will be discussing this until we meet again. May the mass times acceleration be with you.